So now we're going to look at transformers. Okay. Now transformers are devices or electrical devices that are going to change the primary purpose of the transformer. Do not forget this, always remember this, is to change the level of voltage of one supply and change it to another voltage level after crossing through the transformer. But it's not as simple as it looks like. We have to actually understand the mechanism as well. How is it going to happen? Then from that idea, we will develop certain equations and certain mathematical expressions. And in the next class, we will be using those expressions to solve or to at least design a transformer and see where we might find those transformers in daily life. So if it is changing the level of voltage, a simple or a common example of this in your daily life would be your laptop charger. You see, when electricity is transmitted by the electric supply company, it's not their responsibility, and frankly speaking, they can't even do that they would convert all the voltages for you. For example, less voltage for a smaller appliance and a high voltage for a larger appliance. They can't do that. It's not feasible. So what they do is they standardize the output voltage for everyone to use. For example, they may send out 110 to 120 volts in your country, for example, right? And this standard will be followed by all the manufacturers that are providing you with electrical equipment in that country. So if you get a blender, if you get a juicer, if you get a laptop charger, mobile phone charger, any electrical equipment that you're buying from the market, they will have this input criteria. But if the appliance is very large, then this voltage is fine. For example, if you're operating with a very high powered vacuum cleaner, then this voltage would be fine. They do need high voltage, or electric motors do need this voltage to actually operate properly. But if you're charging your mobile phone or your laptop, they are not big devices. They're hardly 200 watts. The laptop averages out at 150 to 200 watts. An average laptop, of course, a gaming laptop would average out at 500 to 600 watts, but we're not talking about that one. So a mobile phone, and an average mobile phone with fast charging, with slow charging, whatever charging there be, is approximately using 20 watts of power, right? So this much amount of power, or this much less amount of power, it shouldn't be fed with 110 or 120 volts. We can't feed this voltage directly to the mobile phone, the laptop. They will actually burn, or they will actually blow out, right? So we need an intermediate device that actually changes, again brings me back to the same point, it changes the level of voltage. Its primary purpose is to change the level of voltage. It doesn't do anything else. Whatever comes after this is a consequence of that, right? So let's try to understand how the transformer, this is what a transformer may look like, right? This slide only represents the evidence of all of this, and does it actually happen or not? This is what we are going to carry out the experiment. But let's move on towards the idea of the transformer itself when it is working, right? So these are two configurations in which the transformer might be given to you in the examination. This silver ring that you see right now is basically an iron ring. And again brings me back to the same point that we discussed earlier. We are using iron because iron is good, or you can say it prefers, or you can say it provides an easier path for the magnetic field lines to pass rather than air. So magnetic field lines would want to pass through iron rather than air. So what we do is we wrap around all the coils around this iron ring, expecting that no magnetic field lines will be lost to air, and all the magnetic field lines will pass through the core, right? So to ensure maximum efficiency. Okay, so how is this working? What's actually happening at the back end? Today we are going to discuss that. So first we go back to the idea of magnetism. If you remember, in magnetism we studied that every magnet is made out of even tinier magnets, which are known as dipoles, and the other names that they have is a magnetic domain. Now these domains or dipoles actually exist inside that element or inside this equipment. If they are sorted out in a single orientation, then I will consider this to be a permanent magnet, or I will consider this to be a magnet. If they are disoriented or they are not aligned properly, then I would have to consider this as an unmagnetized or demagnetized material. Now when we come to iron, these dipoles are already, for example, in random orientations, for the sake of example of course, and let's say they are not pointing out to a simple direction or a single direction. They are arranged in a random order throughout this core, right? Now, when we apply, and be careful, we are applying an AC current. We are deliberately applying an AC current. Why we are doing that, we'll get to that later. So when we are applying an alternating voltage on the input side is called the primary side, always. And the output side, where we do connect the bulb, the fan, the load, the charger, whatever you want to connect, whatever you want to use, this side will be called as the secondary side. So secondary is the output side, and primary is my input side as IP. I just write IP and OP as shorter terms. You cannot write this down in examination. You will refer to them as primary and secondary. So we are applying an AC current or AC voltage on the primary side. So this is the input of my transformer. So why are we supplying an AC current? We'll get to that later. But first we need to understand what's happening if the current is applied to the coil. The coil that we have wound around the core is not physically touching this iron core. They are not. They are insulated. This wire is insulated. What we are trying to achieve is we are trying to force its magnetic field through the core so that it reaches on the other side. You see, if we remember from the last classes, we used the right hand grip rule to figure out the direction of the magnetic field of a coil. So I'm going to use that same rule and curl my fingers in hope to grab this coil and find the direction of that pole. Now, for the sake of discussion, of course, we'll have to get a deeper look at that. We'll have to look at the three-dimensional orientation of the coil, and then we can figure out the direction of the north and south accurately. But we will use the right hand grip rule to do that. Now, for the sake of example, if the current is positive, let's say that the current is moving clockwise like this. And because of that, when I do use the right hand grip rule on the primary side, I find that the north pole is on the upper side and the south pole is on the lower side. But for example, if I go for the negative orientation current, if I go for the negative side, I realize that the current would be moving in this direction. And when I apply the right hand grip rule again, I find that this time around the north pole is at the lower side. So what's actually happening is that the coil, because we are providing an AC current, is deliberately producing a changing magnetic field. So in the previous case, it was having a north pole at the top, and now it is having a north pole at the bottom. This is the benefit of having an electromagnet or a coil, because we can change the orientation of magnets and we can change the orientation of the poles as well. So because of that, because of this changing direction of current or AC current, what's going to happen to the dipoles in the iron core? They are also going to change their orientation. So if, for example, for the positive cycle, we had orientation like this in the core, on, of course, they travel to the other side, make a complete loop, and then flow through the coil. If this is the orientation for the first case, let's say the positive cycle, this is what it looks like. So when the negative cycle is going to come in, the orientation of the dipoles will change. So I'm drawing orange colored representation with the positive cycle and the blue colored with the, or blue colored domains with the negative cycle. So when the negative cycle is going to come into the circuit, so the dipole's direction will change. So if they were pointing towards the left, they will point towards the right. Again, if they're pointing downwards, they will point upwards. If they're pointing right, they're pointing left, left, down, down. So if I analyze this one side of the transformer, what has effectively happened with the secondary coil, which has the load, no supply, no nothing, no power availability, but what's happening with it? You see, if this is my coil and I connect a load with it, in the Faraday's law, we introduced a mechanical magnet motion ourselves to see an induced EMF. This time around, what we are doing this by an automated method. So the coil is experiencing through the iron changing magnetic dipoles. So it is as good as changing magnetic flux. So inside the core, we see that the magnetic flux or the field is changing. And why is it changing? Because we supplied an AC current, right? So since the secondary coil experiences a changing magnetic field, it will also experience an induced EMF. So We provided AC electricity on the primary side, and this has produced an induced EMF on the secondary side without any physical contact, just through the changing of magnetic field and magnetic dipoles. So, do we understand how the transformer would be working now?